Okay. So last time we were talking about square-free monomial ideals. And I was showing you the correspondence between a square-free monomial ideal and a simplicial complex, right? So we said that for our simplicial complex delta, we have the corresponding ideal, which I said is called the Stanley-Riesner ideal. This is in the polynomial ring of n elements. And it's the square-free monomial ideal generated by the non-faces. Right? And we concluded last time by showing this example of the square-free ideal xy, xz. This is a monomial. This is a square-free monomial ideal, so there's a corresponding simplicial complex. And the way we find it is that we say that xy and xz are the non-faces, the minimal non-faces. And so that means that our complex looks like this. And yesterday, I proved the theorem that there was a correspondence between simplicial complexes and square-free monomial ideals. And I stated that there was also a correspondence with unions of coordinate subspaces. Okay? And we did this very carefully in this example. We said that given an ideal, we can define its variety. The variety of the ideal consists of the points let's say P in Fn such that all the polynomials in the ideal vanish at P. Okay. And we saw last time that if we look at the points where the polynomial xy vanishes and the polynomial xz vanishes, then we get the union of two coordinate subspaces, which are the yz plane and the x line, the x-axis in the xyz space. Okay. Now, I want to say a little bit about algebraic geometry, not because this is an algebraic geometry class, but just to give you a little bit of the motivation of what we're going to do next. I told you that there's kind of a correspondence between ideals and varieties, and the correspondence is not one-to-one, but it's close. Okay? Given an ideal, I get a variety. Given a variety, I get an ideal. And these things are almost inverses of each other. Okay? So that means that studying the ideal is more or less equivalent to studying the variety. Now, with varieties, we kind of, varieties are what? They're a new mathematical object, and we like to do the same thing with all mathematical objects. For example, given a mathematical object, how do I split it up into pieces that are kind of indecomposable? That's a very standard thing that we do in just about all of mathematics. And I think you agree that if I asked you to name this variety, then you wouldn't invent a new name. You would just say this is a plane and a line. And a plane is a variety, and a line is a variety. And so this is what's called a reducible variety, because we can say that it's the union of two pieces. Okay? The purple piece and the red piece. Okay? Now, there is a fact, which is that if you have two varieties, let's say V1 and V2, and you look at the polynomials that vanish in the union, then which polynomials vanish in V1 and in V2? Well, they're going to be the ones that vanish in V1 intersected with the ones that vanish in V2. Okay? So what I'm saying is that if I want to consider all the polynomials that are equal to 0 on this variety, which is the union of the purple and the red stuff, then I just have to see what vanishes in the purple stuff, what vanishes in the red stuff, and intersect those guys. Okay? Now, it turns out that the polynomials that vanish on the whole thing, on the whole variety, is precisely the ideal that we started with. What are the polynomials that vanish on the purple plane? Well, this is the YZ plane. And so basically, x is the polynomial that vanishes there. Just x and the multiples of x. Because these are the points that have coordinate x equals 0. And the x-axis consists of the points that have coordinates y and z equal to 0. So the polynomials that vanish there are basically the things generated by y and z. Okay? And so here I have a geometrical fact and an algebraic fact that go hand in hand. So the geometrical fact is that I'm taking this reducible variety, and I'm expressing it as the union of its pieces, of its reducible pieces. What happens to the ideal is that I take the ideal and I express it as the intersection of simpler things. Okay? And this is a general thread in algebraic geometry. This is called the primary decomposition of the ideal. And again, I don't want to go too much into detail in this because that would take us somewhere else. But I want to motivate the next result, which is basically that we're going to do this for the case that interests us. Okay? We're going to give the primary decomposition, we're going to give a primary decomposition of square-free monomial ideals. So let's go back to algebra. What do I want to do? I want to take a square-free monomial ideal and express it as an intersection of simple things. Okay. Turns out that that's pretty easy to do. So what I'm going to do is I'm going to make a definition. Let me define an ideal M super tau. So if tau is a subset of the variables, if tau is a subset of 1 up to n, then I'm going to define M super tau to be the ideal generated by the variables indexed by this guy. Okay, so x I such that I is in tau. Okay. So for example, what I'm saying here is that this guy is just M super 1, and the other one is M super 2, 3, right? And the next thing that I claim is that any square-free monomial ideal can be obtained as the intersection of ideals that are very simple, that are of this form. So here's the proposition. The Stanley-Riesner ideal of delta can be given as the intersection of the ideals m n minus sigma over sigma in my simplicial complex. So this is a very simple combinatorial statement, and let's see what it says here. What it says here is that if I want to do that decomposition for I, then I look at the simplicial complex. I look at the faces of the simplicial complex, which are x, y, z, and then I could also take the smaller ones, like y and z. And then I say, okay, given x, I get an m super all the variables except for the x variable. Okay, so this x gives me m super 2, 3 or yz. And the face yz gives me, I take the complement of those variables, and so I get this guy. Now, in principle, I'm supposed to do this over all faces, right? So, for example, I should also do it for the face y. So for example, y is a phase here, so I should get another guy here, which is which one? M to the variables that are not x. Okay? Sorry, I said y. So the variables that are not y are 1 and 3. So what's the guy that I get here? It's the ideal x, z. Right? So why did I not bother? And I need to do it for the other ones, right? So also, this is x, this is yz, this is y. Then I should also do it for z. So I get xy. And then I should also do it for the empty set. Sorry, so the empty set is a phase here, which means that the complement is what I should put here. So this is the decomposition that is predicted by that proposition over there. Am I confusing you by using 1, 2, 3 instead of x, y, z? I hope that's... If you're confused, where you see a 1, pretend you see an x. Where you see a 2, pretend you see a y. 3 is z. Okay. So this is the decomposition predicted by that proposition. But then when you look at this, you see that I don't need to write all of this stuff because this ideal contains this ideal. Right? And if I already intersect with this guy, which is smaller, I don't need to intersect with this guy, which is bigger. And the same, this guy also contains this guy. This guy also contains this guy, so I don't need this stuff. Okay? I can pretend that this is not here. Okay? And so that means that over here I could also refine this statement and say that sigma is a maximal phase. And I'm going to get that decomposition. So that's the statement. Maybe while I prove this statement, you guys should think about what it says in this case. So let's do another example over here. Let's do it for our favorite simplicial complex so far. So we did several things with this guy. So this is A, B, C, D, E. So the Stanley-Riesner ring, we wrote it down. We said that it's generated by the minimal non-faces, which are these. These are the smallest things that are not faces. And so you should think about what this statement says over here. Actually, you don't need to think about it very hard. Why don't you just tell me what I get? I'm supposed to get an intersection. So what do I get? Can you give me one of them? ED what? So I'm supposed to take all the faces, right? And so for example, Elizabeth, you're taking the face A, B, C. That's a maximal face. So I'm supposed to take the complement of that, which is DE. So that corresponds to the face A, B, C. What else? Give me another one. ACE. So why do we need that guy? Because I have a maximal face, which is the face BD. Right? Then what else? ABE, and that comes from the fact that CD is a maximal face. Anything else? And ABCD, that comes from the fact that E is a maximal face. Anything else? No, right? So these are all the maximal faces. The two-dimensional face ABC, the one-dimensional face BD, the one-dimensional face CD, and the zero-dimensional face E. And so according to this theorem, these things are equal to each other. Okay? So I hope that clarifies the statement of what I'm about to prove. So let's go ahead and prove that. So we're going to just prove both containments. Okay? Now remember something very important, which is that all the ideals that you see here are monomial ideals, right? So by definition, I sub sigma is monomial, but also these m's are monomial. The monomials are very simple. Each generator is just a single variable. Well, that's a monomial in itself. So all of these guys are monomial ideals, and that means that a polynomial lives in these guys if and only if each one of its monomials lives in there. So what I'm going to do is I'm going to say if a monomial lives here, it lives here. If a monomial lives here, it lives here. And that'll be enough. So first let's take one of the monomials that generates here. Okay, so let x sub tau be a generator in the left-hand side. So what that means is that tau is not a face, right? Tau is not a face. By the way, so I guess I'm using a bit of notation here that I haven't introduced, which is that x sub tau is, this is equal to xi1 up to xik, where tau is equal to I1 up to ik. And by definition, that guy is not in that. Okay. So I take a generator of the left-hand side, and I need to find it in the right-hand side. Okay. Well, to prove that it's in the right-hand side, this is an intersection. So to prove that it's in the right-hand side, I would need to prove that it's in every one of these guys that I'm intersecting. So let's proceed by contradiction. So let's suppose that this guy x sub tau is not in here. Okay? And I don't know, maybe we can call this guy xa1 up to xak, where n minus sigma is a1 up to ak. Okay. So what happens? Well, x tau is not in here, which means that xa1 doesn't divide it, xa2 doesn't divide it, xak doesn't divide it. Okay? And what that means is that a1 doesn't live in this set tau, a2 doesn't live in this set tau, ak doesn't live in this set tau. Okay. So basically what I'm saying is that when I look at the set a1 up to ak, which is n minus sigma, none of those guys live in tau, which means that this is a subset of the n minus tau. Right? And what that means is that tau is a subset of sigma. But then if you look at this, this is a contradiction. Why is this a contradiction? Because I said that tau was not a face. Not a face. But delta, by definition, is a face. Right? Sorry, sigma. sigma by definition is a phase of delta. And simplicial complexes are supposed to have the property that if something lives inside them, then all of its subsets live inside. So that's my contradiction. So that shows the first containment. Now for the other containment, again, what I'm going to do is I'm going to take a monomial that lives in the right-hand side. Let's call it like this. Okay. And let's assume that all of these guys actually appear in the monomial, so let's assume that all of these a sub I sub something are at least 1. Okay. In other words, the support of M is I1 up to IK. Okay. Okay. So what does this mean? That means that X I1 to the AI1 up to xik to the aik lives inside each one of these guys m to the n minus sigma. Okay. And what does that mean? Well, each one of these guys is just generated by a bunch of variables. Okay. And so this guy, this monomial, belongs to this ideal if and only if it contains at least one of the variables that appear here. So the support of M contains an element of n minus sigma for all phases sigma. So this is exactly equivalent to saying that the support of M is not a subset of sigma. Okay? You're not a subset of sigma if and only if you contain something that is not in sigma. Okay? And this is exactly equivalent to saying that this guy is not a phase of delta, because first of all, if it were a phase, then it would be contained in itself, and that would contradict this. If it's not a phase, then it cannot be a subset of a phase. Okay? So saying this is exactly equivalent to saying that the support of M is not a phase of sigma. And saying that is exactly the same thing as saying that M is an isodelta. delta. Right, because that means that xi1 up to xik is going to be one of the generators that live in isodelta. delta. So that's the proof. So that's the statement that allows me to take these Stanley-Riesner ideals and write a primary decomposition of them. Now, what does it mean to have a primary decomposition? It means that every one of these ideals is primary. What does it mean to be primary? It means something that is implied by being prime. Okay? So maybe one thing that you should think about for a second is that each one of these guys is a prime ideal. You should have to look up prime ideals and see what they were. But once you do that, it's pretty obvious that this guy is a prime ideal, which means that this really is what I'm calling a primary decomposition. So there's the proof. The most important thing is to realize that this is a tool that allows us to go back and forth from an expression like this being generated by square free monomials to an expression like this being an intersection of these very basic ideals. Okay. So that's the statement that I wanted to make about this. Let's stop for a second and just make a couple of administrative announcements. So the first one is that your homework 2 is graded, and so either you have an email in your inbox, or if you turn it in paper, then I forgot to bring them here, but I will have them in my office, so you can stop by and get your homework. You can turn in your next homework here or by email tonight. And hopefully you all saw that I posted a long list of project suggestions. So there's, I don't know, at least 30 or 40 things that I wrote down there, so there's plenty of ideas of what to do. So you can go to the course website and find project suggestions, and you can go to the forum, and I set up a little thread for you guys to kind of discuss. So if you want to work on something, say it there, and that way, that might be a good way to find a partner. And I should tell you that as I find things, I'm going to keep posting them on the forum. So, for example, afterwards I posted a list of problems that Gubelatse suggested. So that's on the forum. I just got a list from Serkan Hostin, so I'm going to post that there also. I'm going to keep posting things, so keep checking if you want more project ideas. Okay? And if you want project ideas, then this you should really come. Actually, whether you want or not, the colloquium today is going to be very good, and it's related to this class. It's basically the question of solving systems of polynomial equations over the reals, which is what you actually want to do in applications. And so he will actually discuss the kinds of ideals that arise in real life applications and how you deal with them in reality. Kind of have some fast algorithms that actually can do these things. Right, so you should all come to the colloquium, and you're welcome to join us for dinner afterwards. Okay. So that's that. I guess I'll keep this stuff up. And the next thing I want to show is the following. So here's a theorem. I'm basically going to give you a very simple formula for the Hilbert series of any Stanley-Riesner ring. The Hilbert series of the Stanley-Riesner ring. And what I mean by this, remember, is the polynomial ring mod any one of these square free monomial ideals. Is the following thing. We're going to give two versions of this. I'm going to give you, remember that polynomial ring, we have at least two natural gradings for it. One is just the coarse grading just by degree, and the other one is the fine grading that is by multi-degree. And these I sub deltas are homogeneous ideals because every one of the generators is a monomial, and therefore it's homogeneous. And that means that this R mod I is graded and it's actually multi-graded. And that means that I can ask for the normal Hilbert series or the fine Hilbert series. And we're going to give formulas for both of them. So first I'm going to give you a formula for the multi-graded one, and then we will use that one to get the formula for the simple one. So what you do is that you sum over all faces of this simplicial complex the following thing. Actually, I'll just write it like this. That's it. So you should, I hope you already computed the Hilbert series in the homework, since it's due so soon. If you haven't, well, you're in luck, because basically here's a formula. A very nice formula. It just says plug into this and you know what the answer is. And this is the kind of thing that I was telling you is what we're interested in this class. What we were computing, so far we've had very algebraic techniques, right? Free resolutions or things like this. But these ideals are very combinatorial by nature. And so in this case it happens that this question is very algebraic, but the answer is very combinatorial. So for example, what is it in this case? And I think this means that if you already computed it in the homework, you still have time to double check your answer. What is it in this case? Hilbert series of, in this case we have 5 variables, right? And then we're modding out by this ideal. It basically tells you, just go through all the faces of this guy. And for each face, do something. So let's start with the biggest face, A, B, C. So we're supposed to take the product over the elements of element over 1 minus element. So A over 1 minus A, B over 1 minus B, C over 1 minus C. That's the term corresponding to face A, B, C. Now let's go to the two-dimensional faces. Okay? We have a lot of those. So for example, AB is a two-dimensional face, so we get A over 1 minus A times B over 1 minus B. AC is a two-dimensional face, so we get A over 1 minus A times C over 1 minus C. And you have to keep doing this for all of them. So B over 1 minus B, C over 1 minus C, B over 1 minus B, D over 1 minus D, C over 1 minus C, D over 1 minus D. Okay. Those are the two-dimensional faces. Can you do it for the one-dimensional faces? And then you do it for the zero-dimensional face, which just gives you a 1. And that's it. That's the Hilbert series, and that's the finely graded Hilbert series. And realize that these things are generally fairly hard to compute because we have to compute for every single monomial how many things live in that degree. But this is the answer. So this is the first part of the theorem, and then the second part of the theorem is going to go right here. So leave space if you're taking notes. So proof. How do we do this? Well, basically what we're going to do is actually not so different from what Macaulay told us to do, which is that we want to measure this guy in each dimension, R mod I. And so what we're going to do is that we're just going to say that a basis of this guy is given by the monomials that don't live there. So this is something from Macaulay's theorem. A basis for R mod I sub delta is given by the monomials that don't live in delta. Don't live in I sub delta. If you think about this in the way that we drew a picture, we thought of our ideal as being all this red stuff that is above a certain point, right? We had a grid of points here, and then we said that the ideal was taking a bunch of points and just taking all the stuff above, right? So ideals maybe look like this. And so what I'm saying here is basically that if I want a Hilbert series of R mod I, then all I need to do is count the black points, which is what we did actually. Okay? That's what I'm going to do. But the thing is that now we know very clearly what those black points are. Because basically, when is something like x of a, n to the a, x of b, n to the b, up to x sub c, n to the c, in sub delta, and here again I'm assuming that the support of M is all of these variables. Okay. Well, this is a monomial ideal, and so a monomial isn't a monomial ideal if and only if it is a multiple of one of the generators. So xa n to the a up to xc n to the c should be a multiple of one of the generators, which looks like this. X sub tau, where tau is not in delta. Okay? But when is this guy a multiple of x sub tau? Well, x sub tau is a product of some letters, right? X sub 1, x sub 3, x sub 7. And you're a multiple of that if you contain a 1, a 3, and a 7. Right? So this guy is a multiple of this guy if and only if the support contains tau, which is the support of x sub tau for some tau not in delta. In other words, what I'm saying is that a monomial is in I delta if and only if its support contains a non-phase. But again, remember that if I have a non-phase and I add things to it, then I'm still a non-phase, right? Because if I were a phase, then everything that I contain would be a phase. So this statement is exactly the same thing as saying that the support of n is not a face. Okay. So what I showed is that a monomial is in I delta if and only if its support is not a face of delta. And so the consequence of that is that the monomials that I'm trying to count, which are these guys, are the monomials such that their support is a face of delta. So I just need to count monomials whose support is in delta. Now, how can I do that? Well, that's actually fairly simple to do. So maybe I'll leave this picture so you can keep staring at it, and we'll see. I need to make this computation, right? And so now what I need to do is basically for each one of these monomials that is not in I delta is going to contribute to this dimension. Right? Each one of them is going to contribute to the dimension of some graded piece. Now, what does the monomial m contribute to? M looks like this, right? Its degree is NA, NB, and C. And so if you think about this, what I'm looking at computing here is the summation over these guys, which don't live in I delta. And you see, this guy has multi-degree A. And so that means that it's going to contribute 1 to degree A. So I need to add 1 times. Where do I put the things of degree A here? Well, I put them in coefficient x to the A. So in other words, this is all I need to compute. I basically need to compute the sum of the things that are not in I delta. And then I'm going to say, well, let me take that sum. Now, all the things that don't live in I delta have support which is in delta. So what I'm going to do is I'm going to take all the summings in here and I'm going to put them into different groups according to what face is their support. Okay? So for each face in delta, I'm going to consider those guys in this sum such that their support is exactly delta. So I'm just taking this sum and separating it into different summings according to who is the support of the monomial. Okay?
Should not be in I delta?
Yeah. Okay. Now, if you think about this, let's look, for example, at, let's just do a toy example to see what's going on here. So let's say, for example, that we're considering this guy, where the support of x to the a is the set, I don't know, A, B. By the way, this is an if and only if, right? M is not in I delta if and only if the support of M is in delta. So if I already assume that the support is in delta, then I don't need to say that this guy is not in I delta because this implies this. Okay? So that means that I can take this and if the support is a face of delta, then this is for free. Okay? In other words, what I need to do is just sum all the monomials whose support is the set A comma B. Okay? So what do these guys look like? All the different monomials whose support is A, B. So they look like A to the something, B to the something. Okay? So they look like this. And what are R and S? Well, you see, R and S actually have to be at least 1 because the support is really supposed to be A and B. So for example, if I make R equals 0, then all of a sudden this guy would disappear and the support would be B. So when I consider this summation, R and S need to go from 1 to infinity. Okay. And now I need to take the sum. And this is not too bad because I can write it like this. This is the summation from R equals 1 to infinity of the summation from S equals 1 to infinity of this, and then I can use the properties of summation that say that basically because this part only depends on R and this part only depends on S, I can separate it like this. And when I separate it like this, I can see what this is. Because this is a geometric series, right? If it started at R equals 0, it would be 1 over 1 minus A. But it doesn't start at R equals 0. It starts at R equals 1, which means that I should just multiply it by A to get the right answer. So this is A over 1 minus A. And by the same analysis, this is B over 1 minus B. Okay. And so you see the contribution of this term is exactly these things that are popping out in my theorem. A over 1 minus A, B over 1 minus B. That's exactly this term. And I need to do this over all different phases of sigma. So when I make this same analysis for every single phase of sigma, I'm going to get exactly the answer that I want. So that's the end of the proof. So that's the Hilbert that's the multigraded Hilbert series. Now, using that, I can tell you very easily what the coarse Hilbert series is. I just need some definitions. So definitions, the F vector of delta gives me the number of I-dimensional faces of delta. Right? So I make a vector where I say I have one empty face, this many this many points, this many segments, this many triangles, etc. And I make a polynomial out of this guy. So the F polynomial is F delta of t, which is equal to the summation of these guys. So I just make a polynomial out of these guys. Okay. And then the H polynomial is going to be given by this. So it's just some recipe. I just count the number of faces in each dimension, and I build a polynomial like this. Okay. And it turns out then that if I look at the fine grading, where I don't care about all these different variables, I just care about degree, then the answer to this is really nice. All I get is the H polynomial of my SFSU complex divided by 1 minus x to the d. Remember that we had this nice general theorem of Hilbert